This conference will
Good
now be
evening.
recorded.
Yeah, very good evening. Today we'll be learning how to apply perpendicular and parallel axis theorem of moment to calculate moment of inertia of various objects. So in the last class, if you remember, we have already learned what is the definition of moment of inertia. So if we have a discrete object, that means you have an object consisting of n number of particles, then you can calculate the moment of inertia, which is nothing but mass or the particle of the mass and the square of the distance from the axis of rotation. As you can see, this is for discrete object. When you have n number of particles and all of them are separately situated. Okay, so you can calculate the moment of inertia for each particle, or yeah, each particle, and then you can sum them over to get the total moment of inertia of that particular object. But if you have an object which is having a continuous mass distribution, in fact whatever you take in reality, everything, like you just take a disk. Disk means, like, say, yeah, so it has mass all over. If you take a ring also, the ring, like, see, engagement ring kind of those also, so it has masses on the end or periphery, at the periphery, but still it is, this mass is actually continuous. So in such cases, if you want to calculate moment of inertia for continuous mass distribution, so look here, it is actually mass time the square of the distance from that mass distribution to the axis of rotation. So in this case, since the mass is not discrete, it is having a continuous mass distribution, so in that case you have to take elemental mass, and you have to find out the distance of, like, you have to note down the distance of that mass distribution from the axis of rotation, and then thereby you have to do the integration, and obviously this integration limit varies for different shape, size, and different objects. Okay, so in that case we will do integration to calculate the moment of inertia. So this is for discrete and this is for continuous mass distribution. Okay, so now I'll just, for the sake of your recapitulation, I'll just read out the statement of the perpendicular axis theorem and parallel axis theorem, and then we'll go to the application part. So as the moment of inertia of a plane lamina or any planar object about an axis perpendicular to its plane is equal to the sum of the moment of inertia of lamina about any two mutual perpendicular axes on its own plane and intersecting each other at the point where the perpendicular axis passes through. Okay, passes through. So look here in this lamina, x and y, these axes are in the plane of the lamina, and this is actually an axis which is perpendicular to the plane of the lamina. So if you want to calculate the moment of inertia about z axis, so it is stated that the moment of inertia about that particular axis which is perpendicular to the plane of the lamina will be given by the sum of the moment of inertia about any two perpendicular axes. Look, these two axes x and y, they are perpendicular to each other. So moment of inertia about any two perpendicular axes. So this is ix, this is the moment of inertia about x axis, and iy, this is the moment of inertia about the y axis. Okay, so these are two mutual perpendicular axes. So moment of inertia about their about them, if you calculate and then sum them up, you get the moment of inertia about the axis which is perpendicular to let us now go to the next part, parallel axis theorem. So moment of inertia about any axis is equal to the sum of moments of inertia of the body about axis passing through its center of mass and equal to the sum of, okay, so and so this is this one, and the product of the mass of the body and the square of the distance between the parallel axes. So I have taken one object over here, suppose it has mass m totally, and the moment of inertia about axis A, this is an arbitrary, sorry, axis AB, and any arbitrary axis. So about this we have to calculate the moment of inertia. Okay, so to calculate the moment of inertia about this, you need to know the moment of inertia of this particular object about the center of mass. If you know that, then it is easy. So the moment of inertia of that particular object will be object about this AB axis, which is parallel to this axis which is passing through CD axis which is passing through center of mass. So the moment of inertia about the axis AB will be given by moment of inertia about the axis which is passing through the center of mass plus the mass times the product of the square, like mass times the square of the distance. So mass time the square of the distance between the parallel axes. Okay, so look, we'll be applying these two theorems to calculate moment of inertia of various objects. So first I have taken a rod. Okay, we have taken a rod. See, you can see this rod which has a length L. So I have taken a rod having length L. Okay, L. So by symmetry I can just have the axis of rotation. See, this axis of rotation, as you see here, this axis of rotation is actually passing through the center of mass, and it is perpendicular to the length of this rod. Okay, so first let us calculate the moment of inertia. I am writing in short version MOI. Moment of inertia about an axis passing through COM, center of mass, and obviously the center of mass is perpendicular to the plane of this rod. Okay, so rod has length L, and see, as I said, moment of inertia, I'll just write down the definition what we know. Since it is a like this has a continuous mass distribution, I will be applying this m. Okay, so dm into x square. Okay, like this uh, formula I'll be applying here. Look, for that, you have to, as I said, you have to find out first an elemental mass. So I have taken an elemental mass which has a thickness dx, okay, thickness dx, and it is taken from the axis of rotation, which is passing through the center of mass and perpendicular to the length of this rod. So look, this has been taken at x distance from the axis of rotation. So we have considered an elemental length of thickness dx and mass dm at a distance x from the axis of rotation. Okay, now what I have to do, I have to find out what is the del m. So I can write this. The moment of inertia of this particular element will be di is equal to x square dm. Okay, this is for this particular element only. So if you want to get total moment of inertia of this object about of this rod about this axis which is passing through the center of mass, you have to do the integration. Okay, integration of di. Okay, then you will get with a proper limit. So I'll do that. Before that, let me find out what is the dm. See, look, in this case I say uh, the rod has total mass. Suppose a rod has total mass m, capital M, and it has length L, as you can see from here. Okay, so it has total mass capital M and it has length capital L. So I can find out mass per unit length. So what will be the mass per unit length? If I say this is lambda, which is mass per unit length, mass per unit length. So this is small l, obviously. So this is mass per unit length. Mass per unit length. Okay. So if I know mass per unit length is this, so what will be the dm, mass dm here? I'll write it here. You look here. I'll write. So anyway, this will be x square. And what is the dm? Dm I can calculate. See, mass per unit length into dx. So mass per unit length lambda into dx. Dx is the length. I have to calculate the mass for dx length. I know mass per unit length is lambda. So lambda is capital M by L, right? Now I have to calculate the moment of inertia. So if you calculate the moment of inertia from this side to this side, okay, then you can take 0 to L. Okay, you can take limit 0 to L by 2. If you want, see, you can take the 0 to L by 2 so that you get like this, or you can take, see, if you want to calculate the whole for the whole length, then you have to take the limit, see, L by 2 minus L by 2 to L by 2. Okay, so this lambda, I'll just put this here. See, I'll just keep this part alone and then remove all of them. Okay, let me remove all of them. So I have got this expression now. This I have to do the integration. So I have got x square lambda dx, which is dm. Okay, and di is this. Di is x square dm. Okay, so this is what we know. And what is lambda? Lambda also we know, mass, total mass m per unit length. Okay, this is what we know as lambda. We'll put it here and then do the limit. We'll take the limit. I can take the limit in two ways. You can take the limit up to this and you have to multiply 2 to get both side. Okay, or otherwise you can take the whole limit from beginning minus L by 2 to plus L by 2. Okay, so we'll do this itself at a time, at a stretch we'll do. So minus L by 2 to plus L by 2, and this is x square. See, lambda is equal to capital M by L, okay, into this is dx, okay. So this is a constant term. I can take this out, and rest of the thing I'll do the integration for that. So I'll do the integration for rest of the thing, x square dx. So you know this integration is very easy. So if you do this, this will be x cube by 3. So m by L, and look, this is x cube by 3, and you have to put the limit minus L by 2 to plus L by 2. If you put the limit, what you get? See, this is, so if you put the limit, then what you are going to get is, see, m by L, this is L cube by, so 3 I'll keep down here, L cube by 8 minus of minus, that means it will be again plus. So this will be again L cube by 8, okay. So this is what is going to happen here. So what you get, look here. So this will be, eventually I'll just remove here. So this will be 2 of this, okay, 2 multiplied. So if you multiply 2, that's enough here, okay. So this will give you 4. So ultimately what you get, see, this 1 L will be getting cancelled, so it will be L square. So finally what you get here is m L square by 12, okay. This is the moment of inertia about an axis which is passing through the center of mass of this rod, and that axis is perpendicular to the plane of this rod. So I'll just remove everything. I'll write the result what I have got. So about this you will get moment of inertia like this, m L square by 12. Now see, I have to calculate moment of inertia about an axis which is passing through one of the edge of this rod. So this is actually, see, moment of inertia you have to calculate about an axis which is passing through the edge, and it is perpendicular to the length of the rod. So this you can do as I had done earlier. You can do directly, like, see, you can write it I is equal to x square into lambda dx as I had done, and you can take the limit from all the way from 0 to L. You can do this. You can do this in integration. So it will be similar to that. M by L will be, sorry, M by L. So it will be M by L, okay. And if you do the integration, you will get x cube by 3 and 0 to L. Okay, you can just do it in this way also. So if you put the L, so you will get ml square by 3. You can do this in this way, but we are not going to do in this way. We are just going to use the perpendicular axis theorem. So it is easy. If you do also, nothing problem. But we would like to see. So we have got this value. Okay, moment of inertia will be ml square by 3. ml square by 3. Now if you want to get the moment of inertia for this axis, like for this rod about this axis which is passing through the edge and perpendicular to the plane of the rod, by using parallel axis theorem, how to do that? So see, for doing that, you know, the moment of inertia as you know here. So this is actually the axis which is passing through the center of mass for this rod. So I know, you need to know the moment of inertia. See, I have to get, suppose this is some axis AB. So I have to get the moment of inertia about AB. Okay, parallel axis theorem says you you want to get this, so what you have to do, you have to know the center of mass, moment of inertia about the center of mass, plus the total mass of the rod and the distance between this axis. Okay, if this is L by 2, okay, this is L by 2 whole square. Okay, this is what you can do. See, moment of inertia. See, I have already discussed what is parallel access theorem. So if you want to calculate moment of inertia about any axis, you have to first know the moment of inertia about the center of mass, and then moment of inertia about that particular axis AB here will be obtained by taking the sum over, like taking the summation of moment of inertia of that rod about center of mass and this term is the mass time the distance between square of the distance between these two axes. Okay, so look, I know the moment of inertia about the center of mass. Okay, so this is ml square by 12, ml square by 12, and here you get ml square by 4 because the distance is L by 2 here. Look, this much is L by 2. This much is L by 2, and whole mass is m. Okay, so now if you simplify this, so LCM if you do, so you will get here 1, here it will 3, and this is ml square, you know. Okay, so what you get, this is 4, so it will be ml square by 3. So you can do, you like you can use this parallel access theorem, or you can do directly for this system. So at least for this system it is very easy. Even if you don't use parallel access theorem, it is all right. But for some cases we will see it is very difficult to calculate the moment of inertia directly rather than using the parallel access theorem. I'll take up few examples for that. Okay, this is parallel, so this is use of parallel access theorem, but we can use perpendicular access theorem as well to calculate moment of inertia for different shape, like different objects. Let us see. I'll take another good example. So I'll now calculate the moment of inertia of a ring, of a circular ring. What is circular ring? As you can see here, so circular ring actually, see, it has mass only at the periphery of the circle, just like engagement ring or something like that. Okay, so this ring has only mass at the periphery, and you don't have mass in between. Okay, now I would like to calculate the moment of inertia. So for this ring, actually center of mass will be here. Okay, center of mass will be at this point, at the geometrical center of this circle. So this is actually, so moment of inertia which I'm going to calculate about this axis is actually the axis which is passing through the center of mass, and it is perpendicular to the plane of this ring, and sometimes this axis is called as own axis also. This is its own axis, the axis which is passing through the center of mass, because see, it is easy for this ring to rotate about this. It is very easy to rotate this ring about its center of mass. Okay, so that's why it is called its own axis. Anyway, so now look, moment of inertia means it is actually always with respect to the axis of rotation. So as you change the axis of rotation, moment of inertia will be changing. I'll take up few examples like this also. Let me tell you first this particular case. So you have to calculate the moment of inertia about an axis which is passing through the center of mass. Okay, so to do that, suppose this ring has radius r. It has a radius r. Okay, it has radius r. So in this case, you know, I know what I have to do. Integration x square dm, right? So dm, this is what I have to do. Okay, so in this case you look, this x, this is not a variable, because this is the distance from the mass element to the axis of rotation. So since it is a ring, all the mass is always at the periphery of this circular object. So that's why I have to calculate, I have to just consider, an element of mass dm at the periphery only. So I can just take a small element. See, if I have a circle, I can take small element, another small element, and then I can just add all the elements to get the whole. I'll take this much small element. Another element is this much. Another element is this much. So if I add like that, I get a circle. Okay. So I am just considering an elemental length dl, sorry, dx, and it is at r distance, always at r distance. So I just take that this element has mass delta m, okay, and it is at r distance always, so r square dm. So what you have to do, actually you have to do integration of dm. Okay, integration of dm means what? See, if I know this particular element has dm mass, I can take the same element, same shape or same size of element here also having mass dm. I can take another dm. Like that, if I just sum them up, I get the whole mass only. Okay, I get the whole mass, right? So I don't have to do separate integration for that. So this integration will give you, this is nothing but the summation of dm. And when your dm is actually tending to 0, that means when your dx is tending to 0, that means your length of the element is becoming very very small, then that summation actually becomes integration. Okay, according to the definition of calculus. So this thing, whole thing will give you the whole mass of the ring. So eventually what we get is, this is r square, so m r square will be the moment of inertia about an axis which is passing through the center of mass and perpendicular to the plane of the ring. So this is center of mass, like moment of inertia about center of mass. I'll just clean everything and I'll write simply what I get. ICM is equal to m r square. Now see, I I can calculate moment of inertia. See, sometime you might be asked to calculate moment of inertia of the same ring about any of the diameter. You look here. See x. If I just, this is a plane, right? This is in plane. See, in the xy plane, suppose. And see, x-axis if I draw like this, and another axis is the y-axis. If I draw like this, so this x-axis and y-axis will act as diameter. Okay, that means, you know, you can take a ring, you can just rotate in this way also. You can rotate about its center of mass. You can rotate about another diameter like this, another axis which is passing through another diameter like this. You can rotate it any way. Okay, so if you can rotate it, you can calculate the moment of inertia also. Like how easy it will be to rotate any object about any of the, like any ring about its any of diameter. So that is the measure of moment of inertia about any diameter. So look, in this case we will be actually applying perpendicular axis theorem to calculate moment of inertia about any diameter. So what do you know parallel axis theorem? I'm sorry, perpendicular axis theorem. We'll be using here perpendicular axis theorem. Perpendicular axis theorem in this case. So how? Because it is acting as plane lamina. So we know, if I want to calculate moment of inertia about an axis which is passing through the center of mass, which I have taken as IZ, it will be actually the sum of the moment of inertia of any two axes which are mutually perpendicular and those axes are on the plane of the lamina. See, x and y, these are diameter of this ring. They are actually perpendicular to each other, and I cannot take any arbitrary diameter. You have to take perpendicular diameter. Okay, perpendicular diameter. So this angle is 90 degree, and they are on this ring. Okay, now look, since it is symmetric, since this is symmetric, this ring is symmetric, so any diameter you take, moment of inertia will be the same. If I take ix and iy to be id, so both will be actually id. Moment of inertia about diameter will be id. Since it is symmetric at any direction, so moment of inertia for all the diameters will be just id. I am just taking, so it will be 2id right hand side. And you know this thing, right? We have already calculated. What is this? This is the moment of inertia about center of mass. This z is actually passing through the center of mass, and it is perpendicular to the plane of this ring. Okay, so I can write here, so did is equal to moment of inertia about any diameter is equal to iz by 2. What is I did? It is nothing but ICM for the ring, and ICM is what? mr square. We have already got, so you get this. So moment of inertia about any diameter of this ring will be this. Ring will be what? It will be mr square by 2. Okay, about any diameter. Okay, so this is the moment of inertia about any diameter. MOI about any diameter. This diameter. See, now I'll just take another case. So this is this one. As you can see from here itself, here I'll be applying parallel axis theorem. Let me tell you first what is this figure saying. So look, this is actually a ring. The same ring, I have drawn it separately or differently. The same ring which is mass at the periphery only. So I have to calculate the moment of inertia about a tangent which is perpendicular to the plane, which is perpendicular to the plane. That means it is not in this plane. See, this tangent is actually perpendicular to the plane. So you have to calculate the moment of inertia, which is like moment of inertia about an axis which is tangent to the ring, and this tangent is perpendicular to the plane of this ring. So here also, here what you have to do, you can use the parallel axis theorem. Look, in the parallel axis theorem what we have learned, about any axis AB, you can calculate moment of inertia if you know the moment of inertia about center of mass, and if you know, see, the this actually tangent, this is actually tangent which is perpendicular to the axis. Okay, in this situation, perpendicular to the axis. Sorry, perpendicular to the plane of the ring. So this is ICM plus the total mass of the ring and the distance. What is the distance? This is R. R is the radius, so R square. And see, this is actually the axis which is center of mass. See, this is the axis which is passing through the center of mass and perpendicular to the plane. So always you have to find out an axis which is parallel to the axis, given axis, about which you have to find out, calculate or find out moment of inertia. Okay. So in this case, this is moment of inertia. Okay, I'll just do one thing. I'll just clean everything. I'll write what we have already got. This is moment of inertia about center of mass. This is mr square. This is moment of inertia about any diameter. So this is mr square by 2. That is what we have calculated. Now this is actually, you have to calculate moment of inertia about an axis tangent, which is tangent an axis which is a tangent of the ring and perpendicular to perpendicular to the plane of the ring okay, of the ring. So this is what we have to calculate now. See, this tangent is perpendicular to the plane of the ring, and see, this is actually the axis which is passing through the center of mass. Okay, this is also perpendicular to the plane of the ring. So as we have done here, so this I know ICM, center of like moment of inertia will be ICM, which is equal to mr square, and this is parallel axis. This is actually parallel to the center of mass axis. So this axis. So what I can do, I can get, suppose this is AB, tangent is AB. So I can get moment of inertia about AB applying parallel axis theorem. So this is ICM plus m into the distance between the square of the distance between the two axes, so which is r. So square of the distance between two axes is r square. So see, I know mr square, and this is again mr square, right? So what you get from here? Actually 2mr square. You get 2mr square. Okay. Now see, I can take another tangent which is, so I have taken a tangent which is actually perpendicular to the plane of the ring. Now I'll just consider this. So this is actually the moment of inertia about this tangent which is perpendicular to the plane of the ring. Now I can do one thing. I can think this as parallel to the plane of the ring. If this tangent parallel to the plane of the parallel to the plane of the ring, then how you get the moment of inertia? What is the moment of inertia? So this I have got ICM mr square. This is ID, which is actually, see, any axis which is passing through this center of mass, but this is parallel to the plane. See, this is actually ID, any diameter. This is mr square by 2. And look, in this case you have to find out the moment of inertia about this tangent which is in the plane now, in plane of the ring. So in this case also you have to use the parallel axis theorem, but in this case, see, in this case you have to find out another parallel axis which is a diameter. So for any diameter you take, any way you take in this ring, any diameter, you have the moment of inertia this one. So here, when the tangent is parallel to the ring, in that case parallel axis theorem you have to write id plus the distance between the parallel axes. So in this case you look m r square again. Okay, and see id, you know, m r square by 2, and it is plus mr square. Okay, so here you get 3 by 2 m r square. Okay, so this is how you have to calculate moment of inertia. So I have shown you how to apply perpendicular axis parallel axis theorem to calculate moment of inertia of various, like at least for, I have shown you for rod and ring, but there are many such objects like disc you have then you have cylinder, you have cone, you have solid sphere, all those things. But because of time issue, I am not going to discuss those things today. So since you have another class, so I'll stop it here. But we can take a numerical example in some other class to calculate the moment of inertia of any disk, and then disk, then solid cylinder, hollow cylinder, solid cone, hollow cone, and solid sphere, etc. I'll be taking in the next class. Okay. So this is how you have to apply parallel axis theorem, perpendicular axis theorem to calculate moment of inertia. Okay, and this is very important topic for any competitive exam. Wherever you go, at least one question will be there from moment of inertia. Okay, so I'll stop with this for today. We'll be meeting on next week, Tuesday, to have another session on this calculation of moment of inertia, and then there will be few more things to complete this chapter. So bye for today.